Hello everybody, my name is eMoney. Welcome back to my YouTube channel. Last time we covered thermodynamics. We said that thermodynamics is based on the difference in energy between starting material and products, and that Gibbs free energy tells us if a reaction is spontaneous or not. Today we're going to finish the latter half of chapter 6, and here we're going to start off by talking about kinetics. So we know that Gibbs free energy tells us a reaction is spontaneous or not, and that's thermodynamics. What about how fast a spontaneous reaction will occur? Well, the rate, how fast or slow of any reaction, is described by a rate equation. The study of reaction rates is actually called kinetics, and the rate of any reaction will be determined by the rate equation for that specific reaction. Now, here we see a sketch out of a rate equation. K is the rate constant, and it is multiplied by the concentration of our reactants. Now, a reaction constant is specific to each reaction and dependent on a few factors. What are the factors that affect rate constants? Well, first and foremost, the energy of activation. The energy barrier between the reactants and the products is called activation energy. The larger your activation energy, the slower the reaction. And with large activation energies, all right, here you can see a graph of a small activation energy versus a larger activation energy. If your reaction has a lower activation energy, it doesn't take as much energy to get your reaction going, whereas a reaction with a larger activation energy will require will go a lot slower. Now, with large activation energy, you can actually decrease it by adding a catalyst, and a catalyst is something that is going to speed your reaction. Catalysts don't affect the energy of the reactants or products. They simply make your activation energy a lot less, so that the rate of your reaction is a lot faster. Now, another factor that affects your rate constant is temperature. Temperature is another factor, and the higher the temperature, the faster the reaction. And the third thing that is going to affect your rate constant is steric consideration. We're actually going to get to this a little later around chapter 7, but these are the three things that are going to affect your rate constant. Now, this next graph right here is going to help us compare thermodynamics and kinetics. Kinetics refers to the rate of the reaction, while thermodynamics refers to the equilibrium concentration of reactants and products. So your kinetics is the rate of the reactions. It's really affected by this activation energy. This activation energy is going to tell us a lot about how fast or slow. The equilibrium of your reaction is more foretold by the difference in your reactants and products. All right, if delta G is negative, your reaction is spontaneous. If your delta G is positive, it's not so spontaneous. Now, we're going to look at this example, all right, and we're going to determine the spontaneity and the rate of the reaction. So for spontaneity, we're going to try to figure out if our delta G is negative or not. And if it's negative, then it's spontaneous. Now, for the rate, we're going to try to look at the activation energy to kind of predict if this is going to occur at a faster or a slower rate. So what we're going to do is here, we're going to look at this delta G. This delta G looks like it's going to be negative, and so this reaction is going to be spontaneous. The activation energy here is very small, so the rate of this reaction is probably going to be pretty fast. Now, let's look at this one. Delta G looks like it is actually positive, and so this is not going to be spontaneous, but still, again, the activation energy here is pretty low, so it will be a fast kinetics. The kinetics are going to be pretty fast. Here, the delta G is once again negative, and so this is going to be a spontaneous reaction, but is it going to occur pretty fast or pretty slow? Well, the activation energy here is a little bit higher, so this is in relative to the other ones probably going to be a slower reaction. Here again, delta G looks like it's positive, so not spontaneous, and the rate of this reaction, again, pretty high activation energy, so it's going to be a lot slower. So that's kind of how you want to approach this. Now, sometimes our energy diagrams can be a little more complex, like this one right here, because reactions often involve multiple steps. Now, in the energy diagram of a multi-step process, all our local minima, these valleys right here and right here, they're going to represent intermediates in our reaction, and all the local maxima, these peaks that we see here, here, and here, they're going to represent transition states. Now, transition states are defined as high energy species that cannot be isolated. All right, they involve bonds being broken and made at the same time. So in a reaction process, you usually can't extract these transition states, but our reaction goes through them to form products and even to form intermediates. And intermediates are high energy species that can in fact be isolated. They rest at a higher energy state than normal, especially in comparison to reactants and products, but you can indeed isolate them. Now, something that is also important to keep in mind is that we can get from our energy diagrams whether a reaction is endothermic or exothermic. And Hammett's postulate really helps with that. It states that a transition state will be closer in energy to the starting material in an exothermic reaction. Sorry, I zoomed in at the wrong place. Our transition state will be closer to the reactants in an exothermic reaction. And in an endothermic reaction, our transition state will actually be closer to the products. And this is the definition of Hammett's postulate, and it'll help you kind of observing an energy diagram determine an endothermic versus an exothermic process. Now, let's do a quick example problem very quickly, and then we're going to jump into reactivity and stability, which is our last topic for chapter 6. Now, in this question, it says, consider the following energy diagram showing two possible pathways for the reaction between A and B. All right, so we're starting at A and B, and we have two reaction pathways, A and B leading to C and D, or A and B leading to E and F. Those are our two reaction pathways. Based on the energy diagram below, which of the following statements is true? Our first question says, which pathway is kinetically favored? All right, which one of these pathways, AB to CD or AB to EF, is kinetically favored? Now, for kinetics, remember guys, for kinetics, all right, we're looking at our activation energy to determine this. Okay, so which one of these reactions going this way or this way has a lower activation energy? Look how small this activation energy is to this. All right, just purely looking at activation energy, we can tell that the kinetically favored reaction is going to be AB going to CD, because look how small that activation energy is. Now, the second question asks us which pathway would be favorable at elevated temperatures and why? Well, first and foremost, elevated temperatures also help with reactions going faster. But looking at what is more thermodynamically stable here is what's going to really help us answer this question. So which one of these reactions leads to more stable products, ones that are lower in energy? That's again going to be our AB to CD products. So the formation of CD is favorable because the pathway affords more thermodynamically stable products. And so in general, pathway 1 is going to be kinetically and thermodynamically favorable. All right, now we're going to move on to the last part of chapter 7, and this has a lot to do with reactivity and stability, mechanisms in identifying nucleophiles and electrophiles. So here we're first going to talk about reactivity and stability. Now, some molecules are going to want to react with other molecules, and the 4 common indicators of a reactive molecule are formal charges, net dipoles, pi bonds, and steric effects. These 4 indicators are going to help us identify molecules that are going to want to participate in a reactive manner. From this, we're going to learn how to identify nucleophiles and electrophiles in a reaction scheme, and we're going to define these terms. Being able to identify nucleophiles and electrophiles based off of our 4 common indicators is really going to help us learn how things are going to react when they want to react. All right, and then we're actually going to learn how to draw how molecules react, and there's 4 patterns that we're going to learn. We're going to learn nucleophilic attack, loss of a leaving group, proton transfers, and rearrangements, and we really want to spend a lot of time on that last one, rearrangements, because understanding hydride and methyl shifts in rearrangements is very important for organic chemistry. It's going to reappear a lot starting from now. So we really want to understand it fully. All right, so now we're going to start off with that first topic, reactivity and stability. Now, it's good to know that only certain molecules will want to react in a mechanism. But how do we distinguish when and how? Well, we need to keep in mind that stability and reactivity have this sort of inverse relationship. So if a molecule is unstable in some way, it's going to want to react. Now, the obvious follow-up question is, well, how can we tell if a molecule wants to react or not? Well, there's 4 indicators that are going to help us with this. All right, and it's going to go from most reactive trait to least, going from formal charges, all right, net dipoles, pi bonds, and steric effects. All right, if we can determine a molecule is reactive from those 4 indicators, then what we want to do is classify its reactivity more specifically, so we as chemists can have more insight about how exactly it will react. And there's just 2 major subtypes of reactivity. All right, electrophiles and nucleophiles, and now we want to define those. All right, a nucleophile or a nucleophilic center is an electron-rich atom or center that is capable of donating a pair of electrons. All right, so some things that are nucleophilic are features of a nucleophile are inductive effects, lone pairs, or pi bonds. Now, the strength of a nucleophile is very much affected by its polarizability, or in other words, its electron density. An electrophile, on the other hand, is an electron-deficient atom or center that is capable of accepting a pair of electrons. Now, in other words, a nucleophile acts like a Lewis base, and an electrophile acts like a Lewis acid. And again, this table right here shows the features of an electrophile. Again, inductive effects, or having empty p orbitals or positive charges. All right, so let's look at this example right here. All right, keeping the table in place, and let's try to identify if these molecules are first reactive, and if they're going to act like nucleophiles, electrophiles, or maybe even both. All right, this table is from an open source note place called Clutch Prep. They provide empty notes for free. You can go on their website and just download their set of notes. The answers, though, you'll have to subscribe or purchase a membership to find. Okay, anyways, so let's look at this first molecule. All right, is it going to be reactive or not? Well, there's a play on inductive effects here, right? Your chlorine is a lot more electronegative than the carbon it's attached to. So we can draw that, right? this is going to be more partially positive, where this is going to be more partially negative, and this difference is going to make this molecule reactive. It's going to allow it to act as an electrophile. All right, what that means is something can attack this carbon, and this chlorine can act as a leaving group. This leaves this carbon center right here as an electrophile. All right, now let's look at this next molecule, B. Look, it has a positive charge, or in other words, this empty p orbital. All right, this is going to be a reactive molecule. It will act as an electrophile, right? This p or empty p orbital or positive charge is one of the features of an electrophile. All right, let's look at this molecule C. All right, this molecule C has no net dipole. All right, even though it has this chlorine, all right, it has 4 of them. All right, and eventually all these partial positive negatives, all these dipole moments cancel each other out. This molecule is actually very stable and will not be reactive whatsoever, right? Because remember, stability and reactivity have an inverse relationship. This molecule is stable, therefore it will not be reactive. All right, let's look at D. I'm so sorry. It has a double bond. All right, pi bonds are a feature of reactivity specific to nucleophiles. Looking at E, there is a negative charge. All right, lone pairs right there, quite a few of them. Okay, so this molecule is gonna be reactive. That's a feature of a nucleophile. All right. F, this is one that you're going to commonly see, this carbonyl bond, all right? There is inductive effects right here, leaving the carbon with a partial positive, and this partial positive is going to be very prone to getting attacked by a nucleophile. All right, this is reactive. That carbon site serves as an electrophilic center. All right, water is going to be reactive. Water's a very interesting case. Good thing to know, it'll act as both nucleophiles and as a nucleophile and an electrophile. And H, again, we have this inductive effect where the lithium has a partial positive charge. This is going to be reactive, and it's going to behave as a nucleophile as per our features here. All right, so we can categorize almost all reactive molecules, right, as we said, into 2 subtypes. Negatively charged species are usually known as nucleophiles. That's how they commonly appear. Positively charged species are known as electrophiles, and that is how they are commonly known. Fantastic. Now what we want to get into, now that we have defined nucleophiles and electrophiles, let's learn some mechanisms and how to draw the proper arrows for them. All right, we're going to start off with our first pattern, and that's a nucleophilic attack. All right, it's characterized by a nucleophile attacking an electrophile. So your goal is to identify your nucleophile and your electrophile in a set of reactants. All right, and then your action step is to have the nucleophile attack your electrophile. All right, so in this demonstration right here, all right, our chlorine with a negative charge is going to act as our nucleophile, all right, electron dense. Okay, and it's going to affect this electron deficient atom, right, with a positive charge. This acts as our electrophile. So we've identified our nucleophile and electrophile. Now we're going to have our nucleophile, our arrow starting at the nucleophile, attack our electrophilic center right here. And what's going to happen is it's going to attach itself there. All right. Now, with good leaving groups like a chlorine, this reaction can be reversible, right? Because your chlorine can simply leave. With bad leaving groups, all right, like alcohols, for example, it's kind of irreversible. All right, let's do another example problem. All right, now we talked about carbonyls. This is an electrophilic center. Water can act as a nucleophile or electrophile. Here, it's going to act like a nucleophile. All right, and it's going to go ahead and attack our electrophilic center. All right, nucleophile attacks electrophile, and what we get here, all right, is the addition of water. Fantastic. Now let's look at our second pattern, loss of a leaving group. Your goal is to find a group that can leave, a group that is electronegative enough that when it leaves with a charge, all right, it can stabilize that charge. It can deal with that negativity, all right? And the action is, after you find a group that can leave, your electron movement promotes the loss of that group. So here's an example. We have a chlorine here. Chlorine, most halogens are just great leaving groups. They can deal with that the negative charge that they carry. All right, so that chlorine group is going to leave. We're going to move we're going to move electrons as to promote the leaving of this group. So our double bond here is going to move to form a double bond here. All right, and in order to do that, this oxygen has some lone pairs that it's going to dump with the chlorine as it leaves. What we get is something that looks like this, with our positive charge here, and our chlorine group has left. All right, if the leaving group is a good nucleophile, this is a reversible reaction. If our leaving group is a bad nucleophile, it's an irreversible reaction. Let's do an example problem to really understand this. All right, we have a chlorine here. All right, fantastic, great leaving group. Now, how do we move the electrons in this molecule to promote the chlorine for leaving? All right, so what we need is to move electron density as to really get this position right here to meet its octet rule and to kick that leaving group. All right, so if we move the electrons from this oxygen here to form a double bond, all right, and then move this double bond to form a double bond here, which will then move this double bond over here. Ooh, if we move our double bond here, this carbon is exceeding its octet rule and will have to kick off that chlorine group. So we moved the electron density through the molecule. We move those double bonds to get this position to exceed its octet rule and need to kick off a group. All right, and what we get is something that looks like this. And that's how this loss of a leaving group mechanism works. All right, let's go to our third mechanism, and this is proton transfer. All right, so what you're going to find here, what you're looking for, is you want to find the nucleophile and the electrophile. And what is going to happen is that the nucleophile, you're going to find the nucleophile and electrophile, and the electrophile is going to take a hydrogen from. All right, so the nucleophile will steal, the nucleophile will steal a hydrogen from the other. This is very common in reactions, especially to balance charge. All right, so let's look at an example here. All right, our oxygen here is going to have these lone pairs. All right, and this molecule has a positive charge right here. So this is going to serve as our electrophilic center. This oxygen is actually then going to serve as our nucleophile. All right, our nucleophile is going to steal this hydrogen. It's going to form a bond with this hydrogen, and it's going to break off from the oxygen and dump its electrons here. So what we form is water, neutral water. All right, and now this oxygen is going to form a bond to a hydrogen and have a positive charge. All right, these are all technically reversible. Let's do an example problem. All right, this oxygen here has a negative charge. It's going to serve as our nucleophile. What it's going to do is it can steal a hydrogen from the water, and what will form now is this oxygen with a hydrogen bond. All right, and then the water is gonna have a negative charge. Okay, now the last pattern, okay, that we should know for mechanisms is rearrangement. This is the movement of atoms like hydrogens or methyl groups to obtain a stable configuration. And I like to think of rearrangement as changing the interior design of your living room to attain, say, feng shui. All right, some things happen with molecules sometimes, and what you get as a product of a reaction might need some moving around of a hydrogen or methyl group to attain, say, molecular feng shui or stability, in other words. All right, let's focus on carbocation rearrangement here. All right, but let's first look at our carbocation stability chart. Keep that in mind and then do this example problem. All right, so a primary carbocation, all right, a carbon with a positive charge that only has one variable group that's not a hydrogen. All right, this is called the primary carbocation. It's less stable than a secondary carbocation, a carbon with a positive charge and two variable groups that aren't hydrogens. All right, and that's even less stable than a primary benzylic acid, or this is a primary benzylic acid where you have a positive charge next to a ring or a positive charge next to any double bond. All right, and these are less stable than a tertiary carbocation. All right, so here's the trend. Your tertiary carbocation is the most stable carbocation configuration, having a carbon with a positive charge and three variable groups that aren't hydrogens is the most stable form of your carbocation. All right, then you have this next instability, then your secondary carbocation. Your least stable carbocation is your primary one. So keep this trend in mind. Our goal when we look at a molecule and see a carbocation is to ask ourselves if there is a neighboring hydrogen or methyl group that can move there and will result in a more stable carbocation form. Okay, so look at where we're starting here. All right, our carbocation, all right, is at a tertiary, is at a secondary. It's a secondary carbocation, right? It has two variable groups. Can we move anything nearby? Can we move anything nearby like a methyl or a hydrogen to result in a more stable carbocation? Well, let's try this, for example. What if we move one of these methyls over here? All right, if we do a methyl rearrangement, all right, and our methyl group moves here, all right, and we lose our positive charge here, but now we form a positive charge here because we lost a methyl group there. Well, look at this carbocation now. This carbocation is a tertiary carbocation and a lot more stable than a secondary carbocation. So our methyl group will move over to the secondary carbocation position, stabilize it, and now we have our carbocation at our tertiary position and create a more stable carbocation. All right, now our molecule in general is way more stable than it was. Why is this okay, you might ask? Well, the presence of a neighboring alkyl group will want to stabilize a carbocation because a bonding molecular orbital is going to slightly overlap with the empty p orbital. All right, placing some of its electron density in the empty p orbital and resulting in this hyperconjugation that is more stable. All right, so let's do more examples of everything that we have talked about so far. All right, let's do some examples. Now that we know all the patterns of reactive molecules, and now that we know some of the patterns of how molecules will attack each other to form or lose bonds. All right, so let's do this first example. All right, we have an oxygen with a negative charge. This is going to act as a nucleophile. We have this carbon that has a positive charge that's going to act like our electrophile. All right, our nucleophile is going to want to attack this electrophilic center via nucleophilic attack. And what's going to happen is it's going to form a bond. Right here, this oxygen is going to form a bond to this methyl group. Fantastic. Now, here we have a negative charge on our nitrogen. This is going to act like our nucleophile. So that means our water here, in this case, is going to act like an electrophile. All right. What's going to happen here is this nitrogen is going to want to steal a hydrogen from this electrophile. All right. And then dump the electrons there. And so what we are going to form here is a nitrogen, all right, with a hydrogen bond and a hydroxide ion. Fantastic. All right, let's look at example C. We have a double bond here that's going to act like a nucleophile. All right, and what's going to happen is this double bond is going to attack this hydrogen here, and then the hydrogen's going to dump the chlorine as a leaving group. So loss of a leaving group here. All right, what's going to happen here is we're going to form a hydrogen atom here, and this will have a positive charge and your chlorine as a leaving group. Fantastic. All right, so now what we want to do is, for each of the following cases, read the curved arrows and identify which arrow pushing pattern is utilized. Now, the thing is, this is easy. We're just going to identify what kind of pattern is occurring. All right, this might have been a little challenging, right? This nucleophile, electrophile, what's happening here and there. This is going to help. We're going to get better at this as we go through chapter 7 as well. All right, but it's just a simple practice identifying our nucleophiles and electrophiles in a reaction mechanism is really the goal of that previous problem. All right, and the goal of these next problems is kind of to identify reaction mechanism patterns, and we're going to really put it together and get really good at this when we cover chapter 7. So don't worry about it all too much now. Chapter 7, we're going to learn about substitution and elimination reactions, and really the center of how things react with each other and in what way, right? In what pattern, even when we can identify our nucleophile and electrophile, it'll become way easier in chapter 7. So now for this example problem, which of the following cases, all right, for each of the following cases, read the curved arrows and identify which arrow pushing pattern is utilized. All right, we're going to look at A. Okay, we have a hydrogen moving to this position, all right, and our carbocation is moving. All right, this is a carbocation rearrangement. Specifically, all right, specifically it's a hydride shift, right, because we're moving a hydrogen. If we were moving a methyl group like we saw in the example for rearrangement, that would have been a methyl shift. All right, now let's look at B. All right, B, we have this oxygen attacking, this nucleophile attacking an electrophilic center. All right, this is a nucleophilic attack. Fantastic. Look at us go. Let's do a couple more of these, but let's combine patterns of arrow pushing. All right, so we talked about proton transfer, we talked about loss of a leaving group and carbocation rearrangement and nucleophilic attack as our 4 patterns for arrow for reactive mechanisms. All right, so now let's look at multi-step reactions and read the curved arrows and identify the sequence of arrow pushing patterns. So we can look at A. All right, look at that first step. We have a pi bond attacking a electrophilic center. This is a nucleophilic attack, and it's gonna be followed by it's gonna be followed by a, look at that, a proton transfer, right? Because this water is gonna grab on to a hydrogen. So it's followed by a proton transfer, and then lastly followed by a last proton transfer as this oxygen steals a hydrogen from something else. So the pattern for this multi-step reaction is nucleophilic attack, proton transfer, proton transfer. Let's do another one. All right. We have this nucleophile stealing a hydrogen again. All right. That's going to be a proton transfer. All right. The next step is, as you can see, this nucleophilic center, this negative charge, is going to be attacking this electrophilic carbon right here. So that is a nucleophilic attack, and they're going to form a bond right there between each other. Then, as a last step, it seems like our arrow our arrows are moving our electron density to kick out this group ultimately. So this is a loss of a leaving group. So this is kind of how you want to work through these multi-step reactions. Look at what's happening per each step and identify, well, are we having, is a hydrogen being stolen, which is a proton transfer? Are we losing a group, right? And this is like minus group, that's a loss of a leaving group. Are hydrogens and methyl groups moving from one carbocation position to another? All right, that's carbocation rearrangement. Is a nucleophile simply attacking an electrophilic position to form a bond? That's a nucleophilic attack. All right, awesome. So now what we want to do, okay, is practice for each of the following carbocations, determine if they will rearrange, and if so, draw the carbocation rearrangement. Okay, so this is some good practice for carbocation rearrangement because this is so important. Remember, you can have a hydride shift or you can have a methyl shift. So you can move hydrogens to form more stable carbocation configurations, or you can move methyls to form more more stable carbocation configurations. Our goal is to move things to simply get more stable carbocation. All right, keep in mind that this is the hierarchy for our carbocation stability. So let's look at A. A has a secondary carbocation. All right, can we move a methyl group or a hydrogen nearby to form a more stable carbocation? The answer is yes. There is a hydrogen right here, and we can perform a hydride shift. All right, and when we move the hydrogen over, all right, we'll have the hydrogen right there. There will no longer be a positive charge there. Instead, we will have a positive charge where the hydrogen left. And look at that. Now what we have instead of a secondary carbocation is a tertiary carbocation. And guess what? A tertiary carbocation is more stable. So via a hydride shift, we formed a more carbocation stable molecule. All right, let's look at B. All right, B has a tertiary carbocation. All right, we can just end the conversation there. All right, why? Because if we moving a hydrogen nearby over here is simply going to move the positive charge here, and you'll have the exact same tertiary carbocation on either side. All right, so it's already as stable as can be. We have a tertiary carbocation already. If we wanted for some reason to move the hydrogen over here, all we'll get is another carbocation that looks exactly the same. All right, so no shift is going to occur for B. All right, now what about C? C is an interesting case here, all right? Why is it an interesting case? Well, we have a tertiary carbocation already. That is very stable, all right? But we have some methyl groups nearby. And if we were curious to move them over, all right? If we were curious to move, ooh, that's an ugly drawing. If we were curious to move a methyl group over here, all right, and then have our tertiary carbocation at this position. Now, it's still a tertiary carbocation, but it's a little more stable. Why? Because we have a double bond right here to stabilize this positive charge even more. All right, why? This is resonance stable now. We can move the double bond over here and form a carbocation on this side. This area of our molecule now, this carbocation is resonance stable, whereas this carbocation in this position here wasn't resonance stable. So this is very, very stable tertiary carbocation via resonance. So that's something to keep in mind as well, which is why we really wanted to do this problem here. All right, now D. All right, D has a secondary carbocation. There's a lot of hydrogens nearby. You can move them, but all you will form are more secondary carbocations. All right, there's no way to form a tertiary carbocation here, so really no shift will happen here. All right, fantastic. And that is all the practice problems we have for this chapter. We have covered everything. Hopefully this was helpful. If you have any questions, leave them in the comments below and I will try to answer all of them. I hope this was helpful. Happy studying and good luck.